Hello, this is lecture 24, Riemann sums and Riemann integrals. We are gonna start talking about integrals. There's a lot to cover in this lecture. It's going to be quite dense in new content, but hopefully the problems is not they're not gonna actually be so difficult. So first of all, this reminder, what we have discussed already is called indefinite integral, this particular symbol. The meaning that we gave for this symbol is as an antiderivative of the function little f. In other words, something whose derivative is equal to the little f. The goal for today is to discuss what's called definite integrals over, so the definite integral of a function f over an interval ab, it's denoted by basically the same symbol, but you put the endpoints of the interval in here, a and b. And this is going to be a very different thing. This is a number now. The relationship between this and the indefinite integral is only going to come later in a future lecture, not today. So forget about the indefinite integrals and antiderivatives for now. And I'm going to start by talking a little bit about motivation for one thing that we're going to do today, which is given a function, we would like to understand the area under the curve. This is one of the big concepts in calculus. Why is that though? So for example, imagine I have two examples here. Imagine you have a function v of t equals c, representing a constant velocity function. So this is the velocity of some object moving, and it's always equal to this number c. And maybe you want to ask yourself, what is the displacement? How much did the object, how much did the position change between the initial and the final times? As it turns out, well, just think about it. The velocity is always equal to c, and you have, when your velocity is constant, displacement over time. So if you want to compute the total displacement, how much time has passed between times b and a? It's b minus a. And then what is the velocity? It's c. So what is this formula actually? B minus a times c. If you think about this, it's actually equal to the area under the graph. Under in case the c is a positive number. So this is the velocity function, v of t against t. A little graph here. B minus a is the base of this rectangle, and c is the height. The area of this rectangle is giving you the total displacement. But as it turns out, this c could have been negative. An object with a negative speed is just moving backwards. It's moving to the direction opposite to the direction that you call positive. But the formula is still the same for the displacement. It's just going to be a negative displacement, as you expect. And the formula is still some sort of area. So in the case maybe let's call them C1 and C2. In the case that the constant function is equal to the C2 value down here, which is negative, still this expression here still represents an area, but this time it's the negative because this area is now below the t-axis. So this concept of computing area, we usually say under the graph, but there's a implicit meaning that it's actually above the graph if it's wherever the graph is negative, and then you consider that area with a negative sign. This concept appears a lot. For example, right here, when you have a velocity function, this area gives you the displacement. We've just discussed it for constant velocities in this case, but it's true for any velocities. So this is an example of what's called a signed area between the graph and the t-axis. And another example where that happens is maybe you have a function f, also constant, let's say, representing a density function of something over a line. Let's say, for example, you have a distribution of electrons on a line. And then between, once again, you have x now represents position along that line. And f of x is the density of, I say electrons or charged particles because this is something that could be positive or negative, the density of charge along that line. It could be a positive or negative number. If we call that c, then once again, between a and b, the total charge contained into that interval should be, once again, the area under the curve. And what I was saying is that this is true for any sort of density function. It doesn't have to be a constant. So the point is computing area between the x-axis and the graph of a function in this signed way, negative area if it's below, positive area if it's above. This process is important. It appears in many applications. So we're going to be using that as our primary definition of integral. So let f be a continuous function given 2 points a less than b. The definite integral is by definition this number, the signed area between the graph and the x-axis. Well, more precisely, the AB segment. And by signed area, once again, what do we mean? We mean the area of the part of this region above the axis minus the area below the axis. So here's an example. If the red curve is the graph of your continuous function between points little a and little b, then this definite integral between a and b, what does that number represent? It represents the area b minus the areas a and c. That's going to be the definition that we want to think about, at least initially. Later, we're going to give you a more, later today, a more precise definition. And also by definition, this is something that we do by standard. If you flip the two endpoints, instead of integrating from a to b, you do b to a, then the effect of that is just introducing a minus sign in front of the integral. This is the normal one from a to b. So if you flip, you put a minus sign. And also by definition, if you have the same endpoints, a and a, then the integral is 0. So this is a one remark. Other remark that's just like the indefinite integrals, this variable of integration, x in this case, it can be changed to whatever. You can change that to any variable that's not being used, like y or theta, that represents the same number. You do need to have always this d of the variable in the end. It's part of the symbol. It's just there. Remark. So we said the function has to be continuous before. It actually applies to slightly more general functions. The definition also applies to functions that are discontinuous because of just a finite number of jump discontinuities. I have an example down here. Jump discontinuity is when this kind of thing happens, when the graph, it was approaching some number, maybe even tends to that number from the left, but then suddenly it jumps up or down to another number and continues from there. This is a jump discontinuity. So functions like that can also be integrated, and we call them just integrable functions, whatever, continuous functions or maybe discontinuous only with a finite number of jumps. So in this case, this function here, let's say you're going to be integrating between this number a and this number b. You see that you can still define the area between the x-axis and the curve. For example, looking into this range here, you have a sudden drop from this point to this point. The area is along that range would be the area of this piece here, right? So it's just showing you that even though you have jumps, you have discontinuity in the function like that, you can still talk about the area between the curve and the x-axis. So the definite integral is still well defined for this function. Another remark, changing the value of the function at just one number or maybe a finite number of points is not going to affect the integral. It's not going to affect the area. So in particular, when you integrate over an interval, you can say that integrating over the closed interval or open, half closed, doesn't matter. This is all the same. So look back in the example above. Look at this function, for example, this one value of it. This was also a jump discontinuity. One value is kind of off from the graph. There's a hole here. This is completely irrelevant for affecting, in this case, this area down here. Whether or not this point is placed somewhere else or on the location where the graph wants it to be, the area is still the same. So the integral doesn't really see changes like this, just one point. And finally, we already know how to compute some areas from high school algebra or geometry. rectangles, triangles, pieces of circles. So because of this, you actually know already how to calculate the integral for a few functions. Let me give you some examples. This could be an example that we know how to do right now. Calculate this definite integral, where f is this function piecewise. The graph of f is given below. So we want to find the integral between 2 and 8. And here is the function f. So let's only look between 2 and 8. I'm going to be adding more things to this drawing here. We want to find the area between the curve and the x-axis. And we want to take negative if the area is below the x-axis, and positive if it's above. First of all, just by looking at the drawing, you should agree that these are the areas that we're considering. The ones that I'm painting in blue here. So you have basically a rectangle, a triangle, another triangle, and a trapezoid. You need to find the areas of all of these figures and include them with the correct signs. That's going to be your integral. So for example, what's the area of this first rectangle here? It has a base of 1 and a height of 4. So the numeric value of this area, 1 times 4, that's 4. We'll worry about putting the correct sign here later. It's going to be a negative number because it's below the axis, right? But we'll do that later. So you have to do this for all these guys. The little triangle that we have here, for example, well, you first of all, we're going to need to figure out where does this graph cross the x-axis. According to the second piece of the function f, which is above, x minus 4, well, this is equal to 0 when x is equal to 4. This is the number 4 right here. So when you look at this triangle, the base goes from 3 to 4. That means it's 1. And the height goes from 0 to -1. That's also a 1. Base times height over 2. That's the area of a triangle. This is 1/2. You do similar things to all the other ones. All right, so you have 4 to 6, base 2, height also 2. 2 times 2 over 2. That's 2. That's the area. And then finally, the area of a trapezoid. If you don't remember that, you need to take the sum of the bases. You have a base here of 3 and another of 4. So 3 plus 4 times the height. 8 minus 6 is 2. Divided by 2, which turns out to be 7. Given all of these areas, the integral of the function between 2 and 8, integral of f of x between 2 and 8, is, so the 4 and the 1/2 are negative, the 2 is positive, and the last 7 is also negative. And whatever this number is, that's going to be the value of this integral, done by geometry. I have one more example of geometry here. So the function that I'm giving you is square root of 1 minus x squared. We want to integrate it between 1/2 and 1. The graph is below. And suggestion, calling y equals f of x, observe that the curve formed by the graph must be a piece of circumference, since y squared plus x squared is equal to 1. That's just a computation that you can do here. Like if y is f square, if y is f, and then you compute y square. So to get rid of the square root in the f, essentially, then you can rearrange this by moving the x squared to the other side. You see that you get the equation of a circle. However, it's not the entire circle. It's only the positive side of it because we're only taking the positive square root. So all this is saying is that that's how we know the graph of the function is actually a piece of circle. What we want to find in the problem is the integral between 1/2 and 1. That would be the positive of this area here. It's an area involving a piece of a circle. How do we find that area? This is just a little geometry trick. Basically, if you look from the origin to that point on the circumference, this is a point whose cosine is going to be 1/2. So you have to understand this is the 60-degree angle. Cosine equals 1/2. I say cosine because this is down on the x-axis, right? So we know how to compute the area of the entire, let's say like the pizza slice here, this entire figure. This is a piece of circumference. The area of that piece would be, so pi r square, which is just pi, is the area of the whole circle, but that's a piece corresponding to an angle of 60 degrees. So it's something like this. The proportion of 60 to the whole 360, the entire circumference, times the area of the entire circle. That's the area of the pizza slice. What you have to do with this is subtract the area of the triangle. So I'm gonna at least, maybe indicate these guys here. This is that guy. And then the triangle, this triangle right here. That's an easy one because it has base 1/2. And well, what is the height? You can figure that out. It's the sine of 60, which is √3/2. Base times height divided by 2, that's the area of the triangle. When you do the subtraction, you're left with the area they actually want. So I'm not going to simplify this number, but this number represents this integral. Okay, so just be aware for problems like this, problems where you need to use geometry to compute the area. But we're working towards not doing that actually, right? We want to be able to do this for the very usual types of functions that we have, x squared, square roots, logarithms, all of that, where graphs of functions are usually more complicated. How do we actually compute these areas if we know the formula for the function? This is what we are building towards. Okay, one more example using areas. Problem: the graph of a velocity function v of t below shows the numeric value of some indicated areas. So I'm showing you some of the areas on this graph. Compute the displacement of the object between these time instants. The answer is going to fit right here. The problem is just asking you to do this. Remember, well, this is technically v. The function being integrated is v, and the variable is called time, t. But this is what they're asking for when they say displacement. Displacement is the area under the velocity curve. So between 0 and 3, look in the graph. If you're looking only between t equals 0 and t equals 3, you only need to consider the blue and the green areas. And the green gets subtracted because it's below the axis, below the t-axis. Meanwhile, between 2 and 5, there would be the green and the purple, minus 10 plus 30. So these are usually easier problems because you do not have to compute these areas yourself. The curve was not given as a formula, it was just drawn here. But all right, let's move on. So just from this definition as area, there are some properties that we already know should be true. And they are very intuitive. For example, the first one, when you integrate a sum or a difference of two functions, you can split the integrals between them. Sums and differences open up like that. And similarly, when you multiply a function by a constant, c times f, you can bring this constant outside of the integral. This is just like indefinite integrals. Should be very intuitive to think about. So for example, in the second one, when you multiply a function by a constant, that has the effect of scaling the graph vertically. Let's say c is equal to 2. So a function that initially maybe looked like this is now going to look like this, multiplied by 2. So you see that the area has also doubled. Whatever it was, now it has doubled. This is the intuition behind this. But in general, look at item C. Keep this in mind. There are no practical rules for integral of the product and integral of a quotient. They're not equal to the product of the integrals and then quotient of the integrals. That just doesn't happen. Be careful with that. Next property regards the endpoints of integration. If you have the same function f, looking at item D here, same function f in all the integrals here, you go from a to b and then from b to c, then that's the same thing as going from a to c. Very intuitive, basically like this. This is not the only possibility though. A, B, C don't need to come in this order, right? So if you wanted to actually prove this property, you'd have to consider all possible orders for A, B, C. But at least when they are in this order, this is very intuitive to think about. It's basically saying that the area between A and B plus the area between B and C is the area between A and C. Areas add up. Item E, integral of the absolute value of a function. Item E is saying that this integral is actually equal to the total area between the graph and the x-axis with a plus this time. So area above plus area below. Let's actually draw this item E here in front. Let's say you have a function that is positive in some places, but it's negative in some other places. What happens when you take the absolute value of that function? Well, if this is f, where is absolute value of f? Wherever f was positive, it's still going to be the same positive. But now when f is negative, it's going to become positive again. It basically flips the negative part of f back into the positive side. So when you integrate this part, this new function, absolute value of x, well, the red area remains the same. Now the green area, which was negative before, is now positive. That's the point. Initially, the integral, let's say this is a and b. The integral of the original function would be red minus green. But the integral of the absolute value is red plus green. That's what this item is saying. So you may have a few problems related to this property. I don't have any today. I mean, there's not enough time to do problems about every single property, but keep it in mind. Item F, if you have two functions, one less than the other, for all x in some interval, then when you integrate over that interval, the integral for f will be less than for g. At least when a and b are in the correct order. Let's say when that's the smaller endpoint, the a is the one below. Yeah, this is once again very intuitive to think about. You have, let's say, two positive functions, but it's also true for negative or any sign. We're saying that f is always less than or equal to g. Maybe there are a few points where they are equal like this, but it should be very intuitive that the area under the graph of f should be less than that under the graph of g, which includes that area plus more stuff. That's what this item is saying. Item G is similar. If you have a function f, which is always between some number little m and some number big M, then the value of the integral is always going to be between these two particular numbers, mb minus a, mb minus a. What is going on here? Those are areas of rectangles. If you essentially rectangles of base b minus a and height big M and little m. A drawing for that would be like this. Imagine that you have some function between two values, little m and big M. They should technically be positive here. Let's say they are, everything is positive. That's going to certainly be easier to think about. So you have some function between a and b, but it's always between these two values, big M, little m. It doesn't even need to reach those values, although I'm going to imagine it does. Okay, so the integral of the function f is actually this red area. You can see that this red area is smaller than, strictly smaller in this case, this number, big M times B minus A, what is that number? That's the area of the entire rectangle. We can see from the picture that, yes, the area under the graph of F is smaller than the entire rectangle. However, it's larger than this one, little m times B minus A. What is that number? It's the area of the small rectangle down here. That one is an area contained inside of the previous one. So this is once again another property that's true geometrically like this. A quick example about these properties. Suppose you have functions g and h with these properties right here. Compute the particular integrals given. This is going to be very easy. Let's look at item A first. A is asking for the integral of g between the numbers 6 and 2. It's an order that you don't normally see, but that's okay. Well, we know g between minus 5 and 2 and between minus 5 and 6. We should be able to obtain it between 6 and 2. How? Well, just think about that property that says if you want to go from 6 to 2, you can go from 6 stopping at minus 5 and then go from minus 5 to 2. This was one of the properties. So from minus 5 to 2, we already know that's 8. And the other one we technically don't know here, from 6 to minus 5. We know the opposite of that, from minus 5 to 6. So we're going to just flip the first one by including a minus sign. This is what this entire thing becomes. Right, so remember when you flip the endpoints, you have to include an extra minus sign. But now this is all okay. This is going to be minus minus 4 plus 8. So 12. And I don't know why I have item C here. It's item B. The second item is from minus 5 to 2. 3 times G minus 2 times H. So the first thing that you can do is open up like this. The minus between the two functions, this minus can be opened up outside of the integral. All right, and the constants 3 and 2, they can also be brought outside of the integral like this. So now it's just a matter of integrating the functions g and h. We know the integral of g from minus 5 to 2, even though this isn't in the variable x, and it was given in the variable t up here, that's the same thing. So this first one is 8. And then what about the second one? H from minus 5 to 2. Well, we know 2 to minus 5. We know the opposite. This is a 1. So I'm going to write minus 1 down there. Like this. And this is 24 plus 2. So this is the typical problem where you're applying the properties of the integrals instead of actually computing them. But okay, now let's actually start talking about how to compute definite integrals. Computation of areas. The main idea is defined in this first box here. What we're going to do is we're going to be dividing the interval AB into several small pieces. The area in each one, the area corresponding to each small piece is going to be approximated, or I should say the signed area, it's going to be approximated by the small rectangle. You're going to see how this works. A rectangle whose height is determined by the value of f of x for x being some point inside that small piece. And then we're going to add up the areas of all these rectangles. So I have an example here. It's better to just do an example. Consider the integral from 0 to 1 of the function x squared. This is one that we cannot find geometrically. The graph is not going to give you a rectangle or triangle, circle, nothing like that. Divide the interval 0, 1 into 3 pieces of equal length, and then using the value of f of x on the right extreme of each piece, find an approximation to the integral. So item A is telling you First of all, draw a little picture. The function x squared looks like this between 0 and 1. They told you divide the interval 0, 1 into 3 pieces. So the endpoints will involve 1/3 and 2/3. These are 3 pieces, right? Now, consider that above each one of these pieces, there's going to be a rectangle whose height is determined by the function. This problem is all about the right extreme of each piece. What they mean is that, for example, when you're looking at the piece in the middle here, let's say between 1/3 and 2/3, you're going to look at the value of f of 2/3, this value, to give you the height of a rectangle. So this rectangle is the one that you're going to consider in that piece. So you do this for all pieces. The first piece on the right side, it is the number 1/3. F of 1/3 is up here. So you're going to consider a very short rectangle like this. And then the last piece like this. So you see what I mean here by each rectangle has the height determined by the value of f of x, where x is the point on the right side of that piece. If we're talking about the piece between 1/3 and 2/3, the value is f of 2/3. So these are 3 rectangles. If you add up the areas of these 3 rectangles, you should find a very crude approximation for the area below the curve, the area below x squared. I'm going to draw that area in red. Like this is the one that the integral actually represents. The one that we're going to find is a little bit larger than that because it's going to include some extra pieces in green by adding up the 3 rectangles. Okay, but what is it actually equal to? Just add the areas of the 3 rectangles. The first one has a height of, well, what is the height of the first one? If this is the point 1/3 and this point is on the graph of the function, the height here is f of 1/3. So 1/3 squared is 1/9. This is the area of the first rectangle. Second rectangle has an area of what is f of 2/3, 4/9. And the last one is 1. Okay, so you just add up all of this. You can put 1/3 in front. You're going to have like 1 plus 4 plus 9/9. Once again, whatever this number is, this is the answer to item A. This is an approximation to the value of the red area, although it's larger than it because it includes the green areas. Item B is now saying do the same with 6 pieces instead of 3. Let's do that very quickly here. Same picture. You are integrating x squared over the interval 0, 1. But now we're going to divide this interval into 6 pieces. So I have to draw 5 points inside so that there is going to be 6 intervals in here. There are going to be 6 intervals. And for each one of these intervals, let's look, for example, at the one between 3/6 and 4/6. For each one of those, there's going to be a rectangle whose height is, just like in item A, should be the value of the function on the right side of the right end point of that piece, which would be the 4/6 this time. So these are the rectangles that we consider. Be more careful here. Yeah. 6 rectangles. The actual area, once again, the actual value of this integral is the red area that we don't know. We are finding just an approximation for it, which is again larger because it includes the green pieces. What is the area that we are finding? Just add up the areas of the 6 rectangles. Every single one of them has a base of 1/6. And what are the heights? The smallest one is 1 over 36. Then the next one is 4 over 36, 9, 16, 25. The last one is 36 over 36. I'm going to leave this as just like that. So you see what those numbers are, right? They were the values of the function, which is the x squared function. Those are the heights of these rectangles. So I just answered the last question of the problem verbally. I'm not going to write it down on the screen. Do you think the values found above are larger or smaller than the actual value of the integral? They're actually larger. The two values that we found, this one and now this one, they're larger because they include the green areas. This is what the procedure is for approximating an integral. At least it's an approximation, right? This is never going to give you the exact value because you're always going to have some extra piece like that. So this was this problem. I'm going to have exactly the same problem right now as when I flip the page. The only word that's going to be different is this right will become left. So this is the same problem, same function, same interval, but now every time for each rectangle, we're going to be looking at the left extreme of each piece to determine its height. So in item A, we want to use three rectangles, well, three pieces of the interval. So we're going to divide this into 0, 1/3, 2/3, and 1, three pieces. Now let's look, for example, at the middle piece, the one from 1/3 to 2/3. We are once again going to draw a rectangle above it, but this time with a height determined by f of 1/3, which is the point on the left side of that piece. So this is the small rectangle that we are considering. On the last part, the rectangle will have a height of f of 2/3. This is the rectangle. And on the first piece, there is no height, right? The rectangle has a height of f of 0. It's just down here. Okay. So what is the, maybe I'm going to draw this in green here. The sum of the areas of the rectangles, this is the approximation to the integral. The green area is equal to just, it's three rectangles, but one of them has area 0 because it doesn't actually exist. The other ones, they have base 1/3 and heights of 1 over 9 and 4 over 9. Whatever this number is. Do you think this area is larger or smaller than the integral? This time it's smaller. The integral is the entire red area here. We're missing some pieces, right? If we're just considering the green ones. This is a very crude one because we only used 3 pieces. Item B is all about using 6 pieces. So at least you can see that it's going to be a little bit more precise. If you divide into 6 pieces of equal length, 1 over 6, 2 over 6, blah, blah, blah. Draw a rectangle above each one, considering the left endpoint as the one that's giving the rectangle its height. So these are the rectangles that we are considering. Once again, this is going to be smaller than the actual integral, but the areas of the rectangles, we have 6, but the last one, or the first one, has an area 0. What is this green area? Every single one has a base of 1 over 6. And then you have the height of 1 over 36, 4 over 36. The last one, this one has a height of 25 over 36. Okay, whatever this number is, it's going to be smaller than the actual area, which is the integral of x squared. So what are these examples showing us? They're showing you what is called a Riemann sum. I'm going to have some formal definitions here now. So let f be an integrable function, continuous, or maybe it has jump discontinuities on some interval ab. A Riemann sum of f is an expression of this type. It's a sum of a bunch of numbers where each number goes like this. You have f of something times a difference between x values. If we go back to the examples, the difference between x values was always equal to 1 over 6 in this case. We were looking, for example, right here at the, let's say, 3 over 4, 3 over 6 and 4 over 6, these two x values. One minus the other would be the base of that rectangle. It's this 1 over 6. And then we multiply that by the height of the rectangle. In this case, it was f of 3 over 6. So this is what the sum is trying to represent. And then I'm describing what it means. The points xi, these guys, x0, x1, x2, x3, so on, up to xn. You're going to have some n number of them. Those points, they satisfy this. They are between a and b. The first one is a, the last one is b, and then they come in some order. And these points inside of the f with a little star above them, they are just chosen inside of each one of the corresponding pieces. So I'm saying right here, for example, the very first point, x1 star, it's some point inside of the first interval. It does not have to be always the right point or the left point. It could be anywhere inside. So this is what this line is saying. The second point is in the second interval. The last point is in the last interval. Let me draw a picture. This time I'm also going to include negative values for the function because that can happen. You have some function defined on interval between a and b. What we are describing is we are considering a partition of the interval. That's what this is called. Like maybe let's just say 3 points, well, 4 points. x0 is a, maybe here's x1, maybe x2 is right where the function was equal to 0, and then x3 is the last point, which is also equal to b. And then we need to take 1 point inside of each one of the intervals. Maybe x1 star is this point right here. x2 star maybe is right in the middle. x3 star maybe it is equal to x3, as long as it's inside of the third interval. So the corresponding Riemann sum, it represents a sum of areas of rectangles, where you look at f of the star points to be the heights of those rectangles. So I mean, here is the first rectangle. The second rectangle has a height of f of x2 star. I'm going to do that in orange. This is the height of the second, and it spans the base between x1 and x2. Right, so what am I indicating with this? The area of the orange rectangle is height times base. And finally, the third rectangle, I chose x3 star to be exactly equal to x3. The value of x3 star is actually a negative number. So when you consider the area of this rectangle, it's going to be negative. It's going to go into the formula as a negative contribution. But that area is equal to f of x3 star times x3 minus x2. Similarly for the green one. The Riemann sum corresponding to these points is the sum of the areas of these rectangles. And the meaning for that is that it's an approximation to the integral of the red curve. Only an approximation though, right? You can see right here, for example, that you are considering some pieces outside of it, as well as there are pieces inside that you're not considering. The approximation is very crude if you're only using 3 points. But the whole idea is that the more points you use, the better this is going to be. So this is what a Riemann sum is, and we're also going to give some names for special types. The Riemann sum is going to be called the left Riemann sum when this happens. What is this saying? This is saying that for every I, the xi star point, the one that you select to be where the height of the rectangle will be located, is the left side point. So in this case, for example, think about I equals 1, I minus 1 would have been a 0. So we're saying the first point x1 star is x0. It's the left end point of that interval. And that should be true for all the others. Very intuitive, right? You just call that a left Riemann sum. So this is what we did in the last example. Right Riemann sum is what was that was our first example with the parabola, when the x star point is the right side point. And middle Riemann sum, or midpoint, is when your point is right in the middle between the two. Yeah, so we've seen examples of these already, and also the examples we've seen, they are also what's called regular. It's when each one of the pieces has the same length. Let me just look back into this one that I just drew. This one was not regular. It's kind of almost, but not really. If you think about the length between a to x1 versus x1 to x2 versus x2 to x3, those are not exactly the same. If they are exactly the same, then we call that regular. Just like in the last example, remember that we divided the interval into 3 or 6 pieces, which were equal. When we do that, that's called regular. And in that case, what is the length of each piece? We can call that delta x. Just it's the total length divided by the number of intervals. And in that case, you can also give formulas for each one of the points individually. For example, x0 was the first point A. x1 is A plus this delta x, A plus 1 length of a piece. x2 will be A plus 2 lengths of the piece, and so on. So what is regular is when the division between A and B is done in equal pieces. In this case, if A is x0, you have x1, x2, x3, B is x4. The n here is 4. You have 4 intervals. The delta x, the length of each one of them is b minus a divided by 4. And you can see that, for example, x2 is the initial one, a, plus 2 times delta x, because you have 2 intervals before you can reach the point x2. This is what these formulas are saying. Okay, so I'm going to do this problem here and maybe finish this video with it. We can cover the rest of it in recitation. Compute the left, middle, and right regular Riemann sums corresponding to this integral, ln x from 1 to 5, using 4 sub-intervals, n equals 4. This is a equals 1, b equals 5. Okay, so first of all, if n is equal to 4, what is delta x? The length of each one of them. We can do this because they told us regular. Every single piece is going to have the same length. So b minus a divided by 4 is just 1. So what you are doing is, here is the graph of the function, ln x. You know that ln of 1 is 0. So you're dividing the interval between 1 and 5 into 4 equal pieces. The length of each piece is going to be 1. So you know that they must be these pieces between 1 and 2, 2 and 3, 3 and 4, 4 and 5. Each one of these is going to have a rectangle right above it. What is the left Riemann sum? We're not going to give any special symbols for this this construct here. We're always just going to write the words for them. If you see symbols, maybe the book has symbols, but that's not standard. Anyway, what does this mean? It means that in each one of the intervals, you're going to be looking at the left endpoint, calculate f of that in order to determine the height of the rectangle. So for example, in the first one, the base is 2 minus 1, and the height will be f of 1. where f is the function inside of the integral. In this case, it's ln. Okay, so this is the first rectangle. Second rectangle goes like this: 3 minus 2 times f of 2, this one. And then you do this for each one of them. Each one of these bases is always equal to 1, right? You can factor this 1 from everything, and multiply by 1 it's not gonna do anything for you. So this is gonna become f of 1 plus f of 2 plus f of 3 plus f of 4. This is the answer. We don't have to simplify this in any way. Although I'm gonna write, I think I have it somewhere in here, the decimal approximation for what this actually is. This is going to be 3.178. This sum represents, in orange right here, the sum of the areas of these rectangles. And it's actually smaller than the integral of ln x. Okay, what is now the right Riemann sum? You have to do the same thing, but now let's say, for example, in the first interval, the one that goes from 1 to 2, the point that goes inside of f is the point 2, the right point, right end point. So this becomes like this: 5 minus 4, f of 5. The answer will be ln2, ln3, ln4, ln5. Which is approximately 4.78787. A little bit larger, as we expected, because the function is increasing. In general, there is no relationship between left, right, which one is smaller or larger. Not in general, because that's going to depend on the shape of the function. But this function is increasing. So by looking at the right endpoint, let me draw this in green now. The right side of each location where the rectangles are placed. I want to do this like this. Yeah. So by looking at the right side, you're considering slightly larger heights for these rectangles. So it makes sense that this one was larger. And it's in fact also going to be larger than the actual integral. Maybe if I do this very carefully here, yeah, there should not be this little piece of area right here, for example. This should not be there. It meets exactly like this. The value, the height of this rectangle that I just drew should be f of 5, f of 4, right there. Okay, so that's the green. I'm just drawing them so we can see what's happening. I'm not going to draw the last one, but they were also asking about the midpoint Riemann sum. How do we work that one out? This is one where you add the areas of rectangles, but the point that goes inside of f should be the midpoint between the two endpoints of the base, 1 and 2 in this case. You put 1.5 inside. Or technically, you should always prefer to write fractions, 3 over 2. So this is what I'm doing here. 4 minus 3, f of 7 over 2. 5 minus 4, f of 9 over 2. This becomes ln of 3 over 2 plus 5, 7, and 9, which turns out to be approximately 4.079, a number between the two numbers that we found. Because, If you look back in the drawing, let me just draw one of them. For example, the rectangle corresponding to the second piece, the height that we're considering for it is now determined by the number 2.5. It would be a rectangle with this height. You can see right between the orange and the green. All right, so this is the concept of Riemann sums. I'm gonna finish this during recitation because this is now already a very long video. You should try to practice a lot of this. What we're gonna see later is better notation for writing things like this. So when you're writing a Riemann sum, if you're gonna write down every single term like this, it gets complicated because it gets long. It's just too many terms to write. If you use sigma notation, it's a little easier. We're gonna cover that briefly, but the main idea is all in here. Riemann sums, they're gonna be a way of approximating integrals.